Hello and welcome to this presentation related to integration using substitution. Here we solve non-standard integrals not shown in our standard integral tables. This presentation does assume you've seen a previous presentation related to integration using standard forms, where we used a table of standard integrals to solve the various problems. Use of these standard forms contains underpinning knowledge essential to this current presentation. Here's an overview of this integration using substitution presentation. We commence with a brief introduction where we overview the method and we include extracts of tables of standard integrals and differentials. Then we have example 1 where we solve the integral shown here, integral of cos 5x plus 7 with respect to x. If you've seen the previous presentation, you'll know immediately that's not a standard form in our tables. Example 1 is fully worked through. Then we have exercise 1 for you to attempt. Got to solve the integral of 8 minus 3t to the power of 6 with respect to t. Another non-standard integral, but again the full work solution is shown. Then we have some tutorial questions for you to attempt, questions 1 to 9, although the full work solutions will be included. And the presentation concludes with what is termed change of limits. In other words, we're going to solve the integrals not in terms of the original variable, be that x or t, but we're going to use the limits of u, our substitution, and not, for example, x. Tutorial questions 10 and 11 are solved using the limits of u. And here are the approximate start times to the various sections as outlined on this slide, should you want to directly review a particular section, but please note all times are generally rounded to the nearest minute. Just for your further reference, here are the tutorial questions, question 1 through to 5 on this slide. Questions shown here. The answers to each of the questions are shown in these square brackets on the right hand side. Notice that question 4 is a definite integral, so no constant c in the solution, purely numerical answer here. And here are the approximate start times, should you want to directly review the solutions question 1 through to question 5. Again, times are generally rounded to the nearest minute. Tutorial questions continued. Is question 6 through to 9, and again the answers are shown on the right hand side. Just note question 9 is essentially a proof, so the answer is given in the question. And here are the approximate start times to the solutions related to question 6 through to question 9. Just note question 8 does not have a solution, it's left for you to solve at your own pace, but a hint is stated to help generate your solution. Tutorial questions related to the change of limits, question 10 and question 11 shown here, again answers shown in the brackets. And here is the approximate start time related to the start of the solution for question 10, but note there is no solution for question 11, that's left for you to solve at your own pace. Introduction. Here's an overview of integration using substitution. The previous presentation introduced the process of integration for standard integrals, sometimes referred to as standard forms, which were solved using standard tables. However, functions which require integrating are not always in the standard integral form shown in these tables. Here's some reference information from the previous presentation. These are basic extracts here from table 1, or table of standard integrals. And here's the integrand, also the function of x. The main integrands we'll be using in this presentation relate to ax to the n, to 1 upon x, or x to negative 1, cos ax, sin ax, e to the ax, and I'll also show you the standard form function dash x divided by function of x. This is a standard form we can sometimes use in place of integration using substitution. The integrals are shown on the right hand column here. These are effectively our solutions. Just notice with item 1 The ax to the n integrand integrates to ax to the n plus 1 over n plus 1. Add our constant integration if it's an indefinite integral. Note this solution is used for any values of n except when n is equal to negative 1. The integration of 1 upon x becomes ln x plus c, and the integration of cos ax integrates to 1 upon a multiplied by sine ax plus c. Just notice the formatting here. 1 upon a multiplied by the sine ax is actually the same as sine ax divided by a. Sometimes the fraction 1 upon a confuses students in the solution here. You can review the other solutions at your own pace. We will also be referring to our table of standard differentials. Within the integration using substitution process, we will also need to differentiate. Here we have the function of y, polynomial ax to the n, sine ax, cos ax, e to the ax. All these functions will be used in the presentation, and our derivative dy by dx shown here in the right hand column. Notice a sign change when we differentiate cos ax here. And also for reference, I've included the laws of logarithms and the laws and the rules of indices.
Various methods of integration. For non-standard integrals, it may be possible to use one of the following 5 methods to change the function into a form which can be readily integrated using standard tables. So the integration methods available to us include 1. Algebraic substitution, which will be shown in this presentation. 2. Trigonometric or hyperbolic substitutions. 3. Partial fractions. 4. Use of the integration by parts formula. And 5. The use of the reduction formulae. Numerical integration techniques. I'm just going to outline these for reference. It should be realized that many mathematical functions cannot actually be integrated by any of the above analytical methods, and so approximate methods have to be used based upon numerical integration techniques. These methods include the mid-ordinate rule, the trapezoidal rule, and Simpson's rule. These numerical integration techniques are not outlined in this particular presentation, but they are in a separate presentation.
For your reference, there is a separate presentation related to numerical integration where we outline the 3 common rules of numerical integration.
Let's now look at algebraic substitutions used to solve non-standard integrals. With algebraic substitutions, the substitution usually made is to let u equals to the function of x, such that function of u with respect to u is a standard integral. This can then be solved by reference to standard tables. Removing the original variable completely. The most important point when using substitution is that once a substitution is made, the original variable must be removed completely, because a variable can only be integrated with respect to itself. For example, it's not possible to integrate the function of t with respect to x. The integral of 3x with respect to t is not possible. Splitting the differential equation. A concept that du by dx is a single entity, i.e. it measures the differential coefficient of u with respect to x, has been established in previous work in previous presentations on differentiation. When solving integrals and differential equations, du dx is often split, provided that when this is done, the original differential coefficient can be reformed by applying the rules of algebra, then it is in order to do so. For example, if dy by dx is equal to x, then it is in order to write dy is equal to x multiplied by dx, as dividing both sides of the equation by dx reforms the original differential coefficient. In other words, obeys the laws of algebra. Example 1. We're asked to solve the integral of cos of 5x plus 7 with respect to x. Now, given the integral shown in the question, we see that this is not a standard form. because we do not have a cos of ax plus b format in our standard integral table. The closest we have in the table on the previous slides is the integrand, the function of x, cos ax integrated with respect to x. So obviously this is not a standard form. So we're going to try and use the substitution method to make this integral into standard form from where we can use our standard tables to solve the problem. So we're going to make a substitution, and the substitution we're going to try is u is equal to 5x plus 7. What we need to do now is to replace all the x terms in the original equation with u terms. So we have to replace the x with u and the dx with du. So what we need to do is differentiate u with respect to x. So taking the above equation, differentiate the left hand side, we get du by dx, first differential of u with respect to x, and that's equal to, on the right hand side, 5. And to find the 5, we're using the standard differential tables here for the function of ax to the n, which differentiates to the an x to the n minus 1 format. This is something we looked at in a previous presentation. So differentiating 5x to the 1 with respect to x, that becomes 5x to 0, or simply 5, and differentiating a constant, that always disappears. So we get du by dx is equal to 5. If we now rearrange to make dx a subject, we simply multiply both sides by dx and divide both sides by 5. We get dx is equal to du divided by 5. So now we write in the original problem of integral of cos of 5x plus 7 with respect to x in terms of u, we get the integral of cos of u with respect to u divided by 5. If I now take the fifth outside the integral, that becomes 1 upon 5, the integral of cos of u with respect to u. That's now a standard integrand. Item 3 in our table, the cos ax with respect to x is replaced with cos of u with respect to u. So we now have our standard solution. That becomes 1 upon a multiplied by the sine of ax plus a constant c. Then integrating, we have 1 upon 5 multiplied by the sine of u plus c, the constant of integration. What we do now is back substitute for u to find our final solution, which is now be 1 upon 5 multiplied by the sine of 5x plus 7 plus the constant of integration. And what you see in example 1 is a standard process we will now apply to all the questions we're going to look at. We're going to keep it very structured, following the same procedure. Obviously the functions will change, the numerical values will change, but the overall process is as you see in example 1. Exercise 1, we're asked to solve the indefinite integral of 8 minus 3t all to the power of 6 with respect to t. Answers shown in the square bracket on the right hand side here. I would encourage you to stop the presentation and attempt this exercise before reviewing the full solution on the following slides. When you make the appropriate substitution, you'll find you need item 1 in our integral table to help you solve the problem. Exercise 1, here's the solution. We're asked to solve the indefinite integral of 8 minus 3t all raised to the power of 6 with respect to t. And the first thing to note is that's not a standard form. So we're going to try the substitution method. In this case we're going to let u equals to the 8 minus 3t in the bracket. Again, as for the example 1, we have to now replace all the original variables, in this case t, with u. So we need to find du by dt. So on the left hand side, differentiating u with respect to t, we find du by dt, and on the right hand side, differentiate the 8 minus 3t with respect to t, we get negative 3. And again, that's from our standard differential tables. Now rearranging the equation, multiplying both sides by dt and dividing both sides by negative 3, we find dt is equal to du divided by negative 3. All I've done on the final line is brought the negative to the top line, so dt is equal to negative du divided by 3. It's a more conventional way to write the expression. So now our original integral of 8 minus 3t to the power of 6 with respect to t is written as the integral of negative u to the 6 multiplied by du divided by 3. Again, taking constants outside the integral sign, I can take the negative 1 upon 3 outside of the integral to leave me with the integral of u to the power of 6 with respect to u. This is now into standard form. item 1 in our integral table is the ax to the n integrated with respect to x. We've got basically a u to the n integrated with respect to u here. Again, notice there is a 1 in front of the u. We do not write it, but it's there, so our a in this case is 1. Following the pattern through for integrating ax to the n with respect to x, we find we get ax to the n plus 1 over n plus 1 plus the c. Noting that a is equal to 1, so following the pattern through, that now gives us negative 1 upon 3 for a constant, multiplied by u to the 7 divided by 7, plus the constant integration c. What we do now is back substitute for u, so we replace the u to the 7 with the 8 minus 3t to the power 7. Also notice I've tidied up the numerical values. I've got negative 1 upon 3 multiplied by 1 upon 7 from this line here, so that gives me negative 1 upon 21 multiplied by the bracket to the power 7 plus c. All I've done on the final line is to basically multiply the bracket by the negative 1, which is raised to the power 7 in this case, so we end up with 1 upon 21 multiplied by 3t minus 8 to the power 7 plus c. Don't worry too much about that final line, but make sure you can follow the solution down to this line here. Here are some tutorial questions I would strongly encourage you to attempt. We're asked to integrate the following expressions with respect to the variable stated, whether that's x or t or whatever. What you'll probably have noticed from the previous slide, the substitution relates to the bracketed term in the expression. And that's a rule of thumb we can apply in most instances where we see a bracket in the integral, and that's usually what we're going to make our substitution. So for example, in question 1, we're going to substitute for the 3x plus 7. Question 2, again we will substitute for the bracket, make u equals to 2x minus 5, and you will find that the integrand is the form of a type 1. For question 3, we will again substitute for the bracket, the 5t minus 3. When you bring the bracket to the top line, you'll find it has a power of negative 1. And we cannot use the type 1 solution in our integral table when n is equal to negative 1. So what you will find now is this will be a type 2 solution where the u value is to the power of a negative 1. And we'll solve for the ln x plus c function this time. In question 4, we've got an exponential function this time, but again we're going to substitute for the bracket, the power in this particular case, and that will simplify to the standard form of type 16, the e to the ax in our table, which differentiates to e to the ax upon a plus c. Notice in this case this is a definite integral because it has limits on the integral sign, so we'll end up with a pure numerical value when we impose our limits. Question 5 looks more complicated here, but following the principle of substituting for the bracket will make u is equal to 4x squared plus 3. What you should find making the substitution for u is that all the x terms will be removed from the original equation, allowing us to solve the integral in terms of u. This will again be a type 1 solution. In question 6 there's no bracket shown, so we can't in this case substitute for the bracket. However, we could write the sine theta to the power of 5 expression in the question 6 in a bracket that is raised to the power of 5. And now we can see we have a bracketed term, and we would substitute for the sine theta expression. So the key in question 6 is to substitute for sine theta. What you should find is that ends up with a type 1 solution to integrate. Question 7, we substitute again for the bracket here, and you'll find that ends up with a type 2 solution to solve for. And in question 8 we will substitute again for the bracket, and we will find that's a type 1 solution. If you bring the bracket to the top line, it becomes 2x multiplied by brackets 4x squared minus 1 to the power of a negative 1/2. I would strongly encourage you to start the presentation and attempt these questions. The answers are shown in the square brackets on the right hand side against each of the questions, and the full solutions are shown on the following slide. Within the solutions I'll also highlight within question 3 and within question 7 how we could use the item 17 in our standard integral table of the function dash x upon function of x to solve for these problems. Solution of the form ln, the magnitude of the function of x, plus c. So here are the solutions for the questions. Question 1 solution. We're asked to solve the integral of cos in brackets 3x plus 7 respect to x. We're going to use the substitution method in this and all the questions. So the rule of thumb is to substitute for the bracketed term. We'll let in this case the u is equal to the 3x plus 7. It's a very standard solution, very similar to our examples and exercises. I'll let you work through the solution at your own pace and try and come up with the final answer shown here of the third multiplied by the sine of 3x plus 7 plus c. Notice again that there is a 1 in front of the u. We do not write the ones, but they're there. So therefore the a in this case is 1. So note that when you undertake your standard solution for the integral. Question 2 solution, we're asked to solve the integral of 2x minus 5 all to the power of 7 respect to x, and again using substitution. Again we substitute for the bracket, so u is equal to 2x minus 5. Again I will let you wander through a solution at your own pace, try and find the answer that's given here. Question 3, we're asked to solve the integral of 4 divided by the 5t minus 3 in brackets all with respect to t. Again we're using substitution. Again we're going to substitute for the bracket, that u is equal to the 5t minus the 3. Notice in this case we're substituting for the bracket in the bottom line, the denominator, so u is in the bottom line. So to bring it to the top line we have to make it u to negative 1 as found in our indices table shown here in the 5th item. This means we're going to use the second solution in our standard integral table to solve. The x and negative 1 integrates to ln x plus the c. So we'll get the natural log function in our final solution, shown here. Again, I would encourage you to stop the presentation and think through carefully a solution. Here's an alternative approach to solving question 3. So we're asked to solve the integral of 4 divided by the 5t minus 3 all with respect to t. But this time we're solving using a standard form in our table. So using item 17 in our table, we have this standard form which says when the numerator is the first differential of the denominator, using the notation as f dash x in the numerator and fx in the denominator, we're given that the solution is the natural log of the magnitude of the function of x plus the constant of integration. So in this particular case, in the brackets here, we have 1 divided by 5t minus 3. If we were to differentiate the denominator, the 5t minus 3, from our standard tables, we would end up with the value of 5. Now on the top line at the moment, we have the value of 1. So if we could have 5 on the top line, then we would have the standard form where the numerator is the first differential of the denominator. So what I need to do is to multiply the top line by 5, so that when I differentiate the 5t minus 3 on the bottom line, I get 5. And that is the standard form. When you differentiate the denominator, you get the value of the numerator. But because I've multiplied the top by 5, then I must, in this case, multiply the bottom by 5, or else I affect the overall question, and I mustn't do that. So what I'm going to do now is place this expression that we've derived here into the original question given, shown here. So now I have the form that the numerator is the first differential of the denominator. So by multiplying the top and the bottom of the expression by 5, I haven't affected the original problem, but what I have done now is made the numerator the first differential of the denominator. All I've done on the next line is simply taken the constant 5 outside of the integral sign. So don't forget we're dividing by 5 here, so that 5 has come outside the integral sign. That leaves in the integral this expression here, which again complies with the function of dash x over function of x. Now I can simply write down my solution as 4 divided by 5 multiplied by the natural log of 5t minus 3 in brackets plus c. So that's an alternative solution to using the integration using substitution. That's a standard form that's in our tables that we can use, but it needs to be carefully thought through. As you can see, it's how to apply it. Question 4. We're asked to solve the integral of 2 multiplied by e to the 6x minus 1 with respect to x between the limits of 0 and 1. This is a definite integral. If we review our standard tables of integrals, we see the only standard form for an exponential function is e to the ax, and that's not the form we have in question 4. That's more of the form e to the ax plus b. So we're going to try and use substitution to solve this non-standard integral. You'll notice here for the first part of the solution I'm going to ignore the limits and treat the integral as if it's an indefinite integral. I'll impose the limits again on the next slide after the integration process is complete. So on the left hand side I've got the integral given in the question. On the right hand side I've slightly rearranged this. I've just taken a 2 outside of the integral as it's just a constant. I'm now going to make a substitution for the u, and I'm going to make that substitution the 6x minus 1, the exponential power here. So the substitution process, u is equal to 6x minus 1, differentiating for standard tables, du by dx is equal to 6, and then rearranging for dx is equal to du divided by 6. I now substitute my u terms into this equation and simplify, so now I have e to the u instead of e to the 6x minus 1, and that's integrated with respect to du divided by 6. On the next line I simply tidied up the constants. So I've got 2 on the top line and 6 on the bottom line, so taking the 1 upon 6 outside of the integral sign, that gives me 2 upon 6, which cancels to 1 upon 3 multiplied by the integral of e to the u du. I now have my standard form from my standard tables of e to the ax, but don't forget in this case the a is equal to 1 as a 1 against the u we do not write. So our solution is the form 1 upon a e to the ax plus c for an indefinite integral. Note in this case that a is equal to 1, so our solution will be 1 upon 3 multiplied by e to the u plus c. Solution continued on the following slide. Question 4 solution continued. Repeat this line here. We have a third multiplied by e to the u plus the c from the previous slide. If I now back substitute for the u, we end up with the third e to the 6x minus 1, which is our u, plus the c. If I now consider the definite integral with the limits, I no longer need the constant of integration. My integral now on the left hand side is the integral of 2e to the 6x minus 1 with respect to x between 0 and 1. On the right hand side that's now become a third, and in square brackets we've got e to the 6x minus 1 between the limits of 0 and 1. Now I just evaluate my limits. I put the upper limit of 1 into the equation where there's an x, and then I put my lower limit of 0 in this particular case into the equation where there's an x. Simplifying, that becomes e to the 5 minus e to the negative 1, and evaluating we find an answer of 49.348 to 3 decimal places. I would encourage you to stop the presentation and work through a solution on the slide at your own pace. Question 5, we're asked to solve the integral of 3x divided by, in brackets, 4x squared plus 3, all raised to the power of 5, integrated with respect to x. This is a non-standard integral. We would not find this format in our standard integral tables, so we're going to try and solve it using a substitution. So we're trying to solve the left hand side here. All I've done on the right hand side is take the 3, the constant 3 outside of the integral, so I get 3 multiplied by the integral of x divided by the 4x squared plus 3 to the power of 5, all integrated with respect to x. The substitution we'll make this time will be for the 4x squared plus 3 in the bracket, so that's our substitution for u, 4x squared plus 3. Differentiating u with respect to x, we get 8x from our standard differential tables, and then rearranging for dx, we get du is divided by 8x. We now substitute this into the equation, so the 4x squared plus 3 becomes u, so that becomes u to the power of 5, and the dx becomes du divided by 8x. What I've done on the next line is taken the 8 to the front of the integral, so I get 3 divided by 8, and then the x will cancel on the top with the x on the bottom here. And that leaves with the expression of 3 upon 8, the integral of u to the 5 with respect to u. This is a standard form in our tables of ax to the n. Again, note that there is a 1 in front of the u, so the a in this case is 1, and the n is 5. So following our standard solution of ax to the n plus 1 over n plus 1, simplifying numerically, we get 3 upon 8 multiplied by 1 upon 6, and that cancels to 1 upon 16 multiplied by u to the 6 plus the c. All we do now is back substitute for u, so the final solution is 1 upon 16 multiplied by 4x squared plus 3 to the power of 6 plus c. Question 6, we're asked to solve the integral of 24 multiplied by sine theta to the power of 5 multiplied by cos theta with respect to theta between the limits of 0 and pi upon 6. For the first part of the solution, I'm actually going to ignore the limits you'll see from the calculations, and I'll impose the limits later on after the integration process has been undertaken. Also, I've taken the 24 outside of the integral sign to leave me with the sine theta to the power 5 multiplied by cos theta integrated with respect to theta. As I said, I'm ignoring the limits at this particular point in time. Also, when you compare this question to the previous questions, it's slightly different in its format as there's no bracketed term in the expression. In all the previous questions, our rule of thumb was to replace the bracketed term with the substitution u. In this case, we have no bracket. However, if we note that the sine theta to the power 5 can actually be written as sine theta raised to the power 5 in this format, then we can see we have a bracketed term. So we're going to substitute in this particular case u for sine theta. That's the standard form. If we differentiate the u with respect to theta to get du d theta, we differentiate sine theta, it becomes cos theta from standard tables. Rearranging the equation for d theta, that's now equal to du divided by cos theta. We can now replace the sine theta and the d theta terms with our substitutions. So now we get 24 multiplied by the integral of u to the power 5, that's the sine theta to the power 5, multiplied by cos theta from the original expression, and that's multiplied by d theta, which is now du divided by cos theta. We can clearly see that the cos theta on the top line cancels with the cos theta on the bottom line, so that now simplifies to 24 multiplied by the integral of u to the 5 with respect to u. That's now a standard form. In our standard tables, that's the form ax to the n, or in this case x is equal to u. Following the pattern through, given in our solution for the integral, that now becomes 24 multiplied by, in brackets, u to the power 6 upon 6, plus the constant integration, because I'm not considering limits at this particular point. Question 6 solution continued. All I'm going to do now is back substitute for the value of u in the expression on the previous slide, so that now becomes 24 multiplied by, in brackets, sine theta raised to the power 6, or divided by 6, between the limits of 0 and pi upon 6. I now impose my upper and lower limits into the calculation, so imposing the pi upon 6 into the calculation shown here, and then the 0 limit shown here. I'll let you review the calculations at your own pace. What you should find the ultimate answer is going to be 0.0625 or 1/16. Don't forget you need your calculator in radians mode because the angle pi upon 6 is in radians. Question 7, we're asked to solve the integral of x divided by 2 plus 3x squared all with respect to x. This is a non-standard form, so we're going to try the substitution method to solve the integral. In this particular question, we're going to substitute for the bracket 2 plus 3x squared. So u is equal to 2 plus 3x squared, which we differentiate with respect to the x from our standard tables, that's 6x. And we rearrange for dx, that's du divided by 6x. If we now substitute for the bracket and the dx in the original expression, we now have the integral of x divided by u with respect to u divided by 6x. The next line is simplified by taking the 1 upon 6 outside of the integral, that's a constant. And notice that the x term on the top here will cancel with the x term on the bottom here. Notice I've brought the u from the bottom line to the top line and made it u to the negative 1, as we find from our indices table. So our problem now simplifies to 1 upon 6 multiplied by the integral of u to the negative 1 with respect to u. From our standard tables, we find item 2 is the x to the negative 1 solution. We've got u to negative 1 here. So the solution will be ln x plus c for an indefinite integral. Our x is actually u in this case, so our solution will be 1 upon 6, the constant multiplied by ln u plus c. If we now back substitute for u was the 2 plus 3x squared, our solution becomes 1 upon 6 multiplied by the natural log of 2 plus 3x squared plus the c. I would encourage you to stop the presentation and review that slide at your own pace. Here's an alternative solution to question 7 using standard form. We're asked to solve the integral of x divided by 2 plus 3x squared or respect to x. If we consider this expression inside the integral sign, written here for convenience, we've got x divided by 2 plus 3x squared. Now if we look at a standard form of the function dash x over a function of x, This means that if the numerator is the first differential of the denominator, we can write our solution down as ln, the magnitude of the function of x, plus the constant integration c. If we differentiate the denominator here, we will find that 2 differentiated with respect to x becomes 0, and 3x squared differentiated with respect to x becomes 6x. But at the moment, at the top of the fraction, we have x, or 1x, not 6x. However, if we were to multiply the numerator by 6, we would then have the first differential of the denominator. Differentiating 2 plus 3x squared produces 6x. But I cannot just multiply the top line by 6 because that affects the overall question. So what I need to do is also multiply the bottom denominator by 6 so that the 6's will cancel. So if I rewrite now my integral as 6x divided by, in brackets, 6 multiplied by the 2 plus 3x squared, and integrate that with respect to x, I then have my standard form. All I've done on the next line is take the 6, which is in the denominator, outside of the integral, so I get 1 upon 6 now, multiplied by the integral of the 6x divided by 2 plus 3x squared, all integrated with respect to x. Now the integral itself is of standard form of the function dash x over function of x, so I can write my solution down now as 1 upon 6 multiplied by the natural log of 2 plus 3x squared plus the constant of integration. So I've solved the integral here using the standard form and not substitution. I would encourage you to stop the presentation and think carefully through how we made the original integral into standard form and then use the standard form to find the solution.
Here's question 8. We have to solve the integral of 2x divided by 4x squared minus 1, all raised to the power of a half with respect to x. We'll solve this using substitution, but I'm going to let you solve this at your own pace. If you make the appropriate substitution here, which I think is fairly obvious based on our previous work, you'll end up solving the problem in the format of a function of x is ax to the n, although of course we'll actually be integrating the problem in the form of au to the n with respect to u. Here's question 9. We're asked to actually show that the integral of tan x with respect to x is equal to ln of sec x plus our constant integration c. We're given in the question the integral of tan x with respect to x. A hint given here is that we need to realise that tan x is actually sine x divided by cos x. So we will actually integrate sine x divided by cos x with respect to x, and we need to use the appropriate substitution for u in either terms of sine x or cos x. I will show you the full work solution on the following slides. Here's question 9, solution continued. So trying a substitution for cos x in this case, so u is equal to cos x. Differentiating cos x with respect to x, we find that we actually end up with an integral where the sine x terms cancel, and we have an integral in standard form shown here. Basically our x are -1 format, shown here is item 2 in our table, so integrates to ln x, or ln u in this case, plus c. It's actually negative ln from above. And question 9, solution continued. We now back substitute for u, shown here. If you think of this as actually -1 multiplied by ln of cos x, and now we're going to use the third law of logarithms. Third law of logarithms shown here. We're moving from this form to this form. So here we've got the n multiplied by log of a, -1 multiplied by log of cos x, and we're now writing it in the form of log of a to the power of n, ln cos x to the -1, and cos x to -1 is actually reciprocal of cos, shown here. And of course 1 upon cos is actually sec x. So we have a final solution that the integral of tan x with respect to x is equal to ln sec x plus c. That's the full work solution for question 9.
Let's now consider change of limits. In all the previous questions, the limits we were using were in terms of the initial variable, the x of t. We never used limits in terms of u. But let's consider what happens if we want to solve a definite integral, but in terms of the u limits. So when determining definite integrals involving substitutions, sometimes it's preferable to change the limits of the integral, as will be shown in the example on the next slide. For example 2, we're asked to evaluate 4 multiplied by the integral of x multiplied by x squared minus 3 all squared with respect to x between the limits of x is equal to 1 and x is equal to 3. So in the solution, we're going to use a substitution. As usual, we'll substitute for the bracket. So u is equal to the x squared minus 3. We differentiate u with respect to x. So du dx is equal to 2x in this case. And then we rearrange for dx. That's dx is equal to du divided by 2x. If we now substitute in the original equation for x and dx, we have 4 multiplied by the integral of x multiplied by u squared, the bracket squared, and that's multiplied by the dx, which is now du divided by 2x, between limits of 1 and 3. Notice the x on the top line cancel with the x on the bottom line, so the whole integral simplifies now to 2 multiplied by the integral of u squared with respect to u between limits of 1 and 3. But the problem here is that the limits are in x and not u. So we cannot solve the integral in terms of u and impose the limits of 1 and 3 because we get the wrong answer. So what we could do here is change the limits of the integration. Instead of using our limits in terms of x, we could use our limits in terms of u. So noting that u is equal to x squared minus 3, our original substitution here, then when x is equal to 3, putting the value of 3 into this equation, we find u is equal to 6. And when x is equal to 1, put the value of 1 in the above equation here, we find that we get u is equal to negative 2. Now we can solve the integral with the limits of u. So 2 multiplied by the integral of u squared with respect to u between limits of negative 2 and positive 6. We find that solving the integral, that's 2 multiplied by, in brackets, u to the power of 3 divided by 3 between limits of negative 2 and 6. Evaluating the integral by imposing the upper and lower limits, we find the value of 149 and a third. If you wanted to check this using the limits of x, you could back substitute here for the value of u and then impose the limits of x is equal to 1 and x is equal to 3. You'll get exactly the same answer. Here are some tutorial questions related to the change of limits. So question 10, we're asked to solve this equation and using the limits in terms of u, and question 11 the same, as to solve the equation there given in terms of the limits of u. Notice the answers are given here on the right hand side of the question. I suggest you stop the presentation and undertake these questions now. Solution for question 10 is shown on the following slide. Question 10, solution shown here. I'll let you review the solution at your own pace. In this particular case, we're going to change the limits of theta from theta is equal to 3 to u is equal to 25 and theta is equal to 1 to u is equal to 9. I'll let you work through a solution. You should find the answer is 81 and 2/3. Here are some further tutorial questions I would encourage you to undertake. Questions 1 through to questions 10, and the answers are shown in the square brackets on the right hand side of each question. Here's the bibliography used to help generate the presentation. Very good textbooks written for technicians. I hope this presentation has been enlightening to you, and thank you for viewing.